We have seen that by the arbitrage pricing theorem, the bond price processes discounted by the savings account are martingales under the risk-neutral measure. In this part, we will now learn that if we discount bond price processes by a specific T-bond, then this will give us martingales again, but under some equivalent measure that is called the T-forward measure. This change of numeraire technique proves most useful for option pricing with stochastic interest rates. As an application, we will derive closed-form formulas for options on bonds in the Gaussian Heath-Jerome-Morton framework. As a setup, we consider a filtered probability space with risk-neutral measure Q, which is equivalent to the real-world measure P. On this stochastic basis, we are given a short-rate process and the T-bond price processes which are given by the arbitrage pricing theorem in this form. Such that the T-bond price process discounted by the savings account is a martingale under the risk-neutral measure Q, as becomes evident here. Moreover, this martingale is strictly positive, so that after normalizing it, we can use it as a candidate for a radon-Nicodim density process for an equivalent measure. We call this measure the T-forward measure, denoted by Q index T. It is equivalent to Q with a radon-Nicodim density process given by the normalized T-bond price process discounted by the savings account. Normalizing means that this martingale in expectation is equal to 1. The T-forward measure is defined on a time horizon T. At this terminal time, the density is simply given by the reciprocal of the savings account times the normalizing factor. Here is an important application in derivatives pricing. Consider a claim that is due at time capital T, and suppose the payoff is given by X. The price at time small t is given by discounting the payoff X with the savings account and take the conditional expectation under the risk-neutral measure Q. The difficulty for computing this expectation comes from the fact that the argument is the product of the discount factor times X. Using the T-forward measure, we can re-express this expectation of the product of the discount factor times X as expectation of X only. The expectation is taken under the T-forward measure, and the expectation has to be normalized by the prevailing price of the T-bond. To equate these two sides, the Q conditional expectation and the QT conditional expectation of X, we use Bayes' rule as shown here. Here is a fundamental property of the forward measures. For any time points T0 and T1, the T0 bond price process discounted by the T1 bond is a martingale under the T1 forward measure. Strictly speaking, this martingale is only defined up to the time which is given by the minimum of T0 and T1. Again, this claim can be proved using Bayes' rule as shown on this line here. As a consequence, the simple forward rate for the future time interval t0, t1 follows a martingale under the t1 forward measure. This follows from the relation between this forward rate and the ratio of the t0 bond price divided by the t1 bond price. Because it is a martingale, it can be written as conditional expectation of its terminal value at time t0, which is simply the future simple spot rate. We can say more in a specific model. So let us consider the Heath-Jerome-Morton framework, where the t-forward rate dynamics under the risk-neutral measure Q is given as shown here. This is simply rewriting the Heath-Jerome-Morton drift as we have seen it previously, using the bond return volatility V, which is defined as minus the integral of the forward rate volatility sigma. In such a Heath-Jerome-Morton model, we have also seen that the discounted bond price process can be written as stochastic exponential as shown here. So we are given an explicit expression for the radon-nicodym density process of the t-forward measure in terms of the Brownian motion W star under the risk-neutral measure Q. We can then apply Girsanoff's theorem that implies that under the t-forward measure, the process that we call W upper index capital T, which is defined as shown here, is a Brownian motion. It then follows immediately from this representation of the t-forward rate dynamics that the t-forward rate process is a martingale under the t-forward measure, and as a consequence it can be written as conditional expectation of its terminal value, which is just the future short rate at time capital T. Now let us look at the most basic option in the bond market. It is a European call option on a T1 bond with expiry date T0 and strike price K. This option gives the holder the right to buy a T1 bond at the expiry date T0 for the price K. The holder of the option will exercise the option only if the T1 bond price at expiry date T0 is larger than K. As a consequence, the payoff to the holder of the European call option is given by the positive part of the difference of the T1 bond price at time T0 minus K. We obtain the price of this call option at time 0 by discounting the payoff with the savings account and take expectation under the risk-neutral measure. We could compute this price for any time small t prior to T0, but for simplicity of notation, we concentrate here on the spot date 0. We see again that the difficulty for computing this option price comes from the fact that the argument in the expectation operator is the product of the discount factor times the payoff, which is random variable, which is measurable with respect to ft0. We could, as seen on the previous slide, get rid of the discount factor by rewriting this expectation as an expectation under the T0 forward measure, but we will do something smarter here. We denote in blue here the exercise event of the call option. That is the set of all states where the holder of the call option will exercise the option. This is exactly when the T1 bond price is greater than the strike price K. We can then decompose the payoff of the call option into the difference of the T1 bond price times the indicator function of the exercise event minus the strike price times the indicator function of the exercise event. We then use the linearity of the expectation operator and can write the call price as the difference of the expectations of the respective components. We then change to the T0 forward measure for the second expectation to get rid of the discount factor as shown here. And we end up with the expectation of the indicator function of the exercise event under the T0 forward measure, which is simply the same as the probability of the exercise event under the T0 forward measure. In the first expectation, we observe that this factor that I underline here, after normalization with the initial T1 bond price, is the same as the radon-nicodym density of the T1 forward measure conditional on T0. This is just what we need to apply Bayes' rule again and re-express this first expectation now as expectation of the indicator function of the exercise event under the T1 forward measure, which is nothing else than the probability of the exercise event under the T1 forward measure. As a result, we summarize that the call option price of a T1 bond with expiry date T0 can be expressed in terms of the probability of the exercise event under the T1 forward measure and the T0 forward measure. So, in order to find a closed form formula, we have to formulate a model for which we can compute these two probabilities in closed form. And this will be the case in particular for Gaussian Heath-Jerome-Morton models. As an intermediary step, we observe that the probability of the exercise event under the T1 forward measure can be rewritten as probability of an event that is expressed in terms of the T0 bond price discounted by the T1 bond price. Similarly, the probability of the exercise event under the T0 forward measure can be rewritten as probability under the T0 forward measure of an event expressed in terms of the T1 bond price divided by the T0 bond. Now this is useful observation because we know that bond price processes discounted by the T1 bond are martingales under the T1 forward measure, and similarly for T0, bond price processes discounted by the T0 bond are martingales under the T0 forward measure. That means in both cases we have here the terminal value of a martingale under the respective forward measures. In the Heath-Jerome-Morton framework, we can even write down how these martingales look like. The T0 bond price process discounted by the T1 bond can be written explicitly as a stochastic exponential of a stochastic integral with respect to the Brownian motion under the T1 forward measure. And this holds interchangeably for T0 and T1. Now, in view of these two identities, it should be clear that when the volatility is a deterministic function, the stochastic exponential is a log normal random variable. We can compute its mean and its variance, and so we will be able to compute this probability in closed form. And similarly, interchangeably, T0, T1, we will be able to compute this probability. And here are the details. Assume that the volatility sigma is a deterministic function, and so consequently the bond return volatility is also a deterministic function. We can go back to the stochastic exponential shown on the previous slide and take the logarithm, which gives us this identity as shown here. Because v is a deterministic function, we know that what we have on the right-hand side is a Gaussian process. The mean function is given as shown here, and the variance function is given as shown here. Setting small t equal to T0 and combining this insight with the previous slides, we arrive at the following theorem. In a Gaussian His-Geromorter model, that is, a His-Geromorter model with deterministic volatility function sigma, the time zero price of a European call option on a T1 bond with expiry date T0 and strike price K is given by the difference of the T1 bond price times the probability of the exercise event under the T1 forward measure minus strike K times the T0 bond price times the probability of the exercise event under the T0 forward measure. These two probabilities can be written as standard cumulative distribution function phi evaluated at D1 and D2 respectively, where these numbers are given by the expression shown here. This is a closed form formula for the price of a European call option on a bond. From it, we can easily now infer a price formula for a European put option on a bond, as shown in the following. The put-call parity relates call prices to put prices in a one-to-one relation. It derives from this elementary identity. Here is the payoff of a call option, and that is the payoff of a put option with the same strike K. By linearity of the prices, we infer that the difference of the call price minus the put option price is given by the present value of what we have here on the right-hand side, which is simply the T1 bond price at time 0 minus K times the T0 bond price at time 0. We can solve the put-call parity for the put option price and plug in the call option price from the previous slide to derive that the put option price in the above Gaussian His-Geromorter model is given by the expression here. From the put-call parity, we also see that the put option price is equal to the call option price for a specific strike price K given by the T1 bond price divided by the T0 bond. The strike price is called the at-the-money strike price. As an example, let's look at a specific Gaussian His-Cheromorton model, the Vasicek short rate model. We already know that the forward rate volatility function is given as shown here. We can then explicitly compute the difference between the volatility of the return on the T0 bond minus the volatility of the return on the T1 bond, as shown here, such that the integrated square difference of these volatilities is given as shown here. This is one ingredient of the above Gaussian HGM model call option price formula. The other ingredient is the initial discount curve. We thus obtain an explicit closed form bond option price formula in the Vasicek short rate model. For an illustration, we choose the parameters as shown here. For these parameters, we compute the put option prices on the TI bond with expiry date TI-1 and the at-the-money strike price KI, which is given by the ratio of the TI bond price divided by the TI-1 bond price. We do this for a sequence of expiry dates and bond maturities going from 1/4 of a year up to 10 years. We obtain a term structure of put option prices as shown in this graph here. The scale on the y-axis is in basis points. This means the price of a put option on the 1/2 year bond with expiry date in 3 months is slightly less than 4 basis points.